So let's talk about this other class of isomers that we have not discussed yet. Isomers that contain asymmetric centers. We'll define asymmetric centers in a moment, but before that, let's define chirality. What does it mean to be chiral? A chiral compound is a compound that has a non-superimposable mirror image. What does that mean? Non-superimposable means pick up the mirror image, see if you can rotate it, manipulate it in any way to fit and match the original compound. If it does not fit, does not match, that's called non-superimposable. A compound could also be achiral, as in not chiral. A compound that has a superimposable mirror image is an achiral compound. Okay, how can we tell the difference? Well, one way that we can tell the difference is in a lab. If you set up a contraption like this down here, this contraption, actual instrument, is called a polarimeter. Set up a polarimeter, you have a light source. Light from all natural light sources come in all directions. The light waves coming out of that light bulb are in all kinds of directions. If that light passes through a polarizer, you've heard of polarized sunglasses, that light passes through a polarizer, what you get out of it is plain polarized light. Light in only a single direction is allowed to pass through. If that light passes through a chiral molecule, the light direction shifts. The molecule interacts with the light to cause the wave of the light, the direction of the wave of the light, to shift, to rotate. We would say a chiral molecule would rotate plain polarized light. A shorter way of saying that is we would say a chiral molecule is optically active. If in this tube you had an achiral molecule, that would not rotate the plain polarized light. The direction that it goes in is the same as the direction that it comes out. So that's said to be optically inactive. That sounds super nerdy, sciencey. I'm not sure what application that has to real life. Well, this is thalidomide. Thalidomide has one of those asymmetric carbons that was on our isomers flowchart in the beginning. What the heck is an asymmetric carbon? An asymmetric carbon is a carbon that's bonded to 4 different groups. We'll explain that definition better in a moment, but right now we're trying to figure out why do we care about chirality. So a compound that has a single asymmetric carbon exists as 2 different stereoisomers. Those 2 different stereoisomers are called enantiomers. Those enantiomers can have different names, different letter designations, R and S. We will talk about that. Bear with me. So those 2 enantiomers have different designations, R and S, and they can potentially do different things in our bodies. Thalidomide is a drug that was prescribed to pregnant women in the 1950s. It was prescribed as to help their morning sickness. This sedative action of the R enantiomer was very helpful to their morning sickness. But thalidomide was not investigated as fully as it should have been because, as it turned out, the S enantiomer was a teratogen. If you don't know what teratogen is, it's responsible for birth defects. So there were many kids born in the 50s that were without limbs because their mothers, when they were pregnant, had been prescribed thalidomide, a mixture of thalidomide enantiomers. It's a really sad story. That's one reason we should care about enantiomers and asymmetric carbons and chirality and all that stuff. So pharmaceuticals all depend on a biochemical recognition in our bodies. A biochemical recognition means when 2 components bind together to initiate some sort of biochemical event, as in suppress certain things or promote other things, etc. The 2 things that have to come together are an enzyme and a substrate, or receptor and a substrate, like cell receptors and a substrate. A substrate is just a fancy word of saying a molecule. But that molecule usually needs to have an appropriate shape, because the shape of the molecule needs to fit precisely into the shape of the enzyme in order to do what you need that compound to do. If you have some cleaning gloves, like rubber cleaning gloves, the thick yellow kind, that glove only fits one hand because your hand can be considered chiral and that glove can be considered chiral. Like an enzyme and a substrate, your hand only fits in one glove. Pharmaceutical developers need to make sure that the drugs that they are making are appropriate for the enzymes in our bodies. They're the appropriate shape. Pharmaceuticals is one of the easiest places to talk about it, but molecules like this also matter. This carbon down here is the asymmetric carbon. We're going to define it better in a minute, refine the definition better in a minute. But this is carvone. Carvone has a single asymmetric carbon, and anything that has a single asymmetric carbon has two enantiomers. The R enantiomer of carvone smells like caraway seeds. The S enantiomer of carvone smells like spearmint. That's because the molecules R and S have different shapes. R's and S always have different shape because they're stereoisomers. They're different in three-dimensional space. But the shape of S fits a certain receptor in your nose. That makes your brain register, oh, that's spearmint. The R enantiomer fits a different receptor and your brain registers, oh, that's not spearmint, that's caraway. So these are not pharmaceuticals. These are spices, herbs, whatever you call those things. They smell different because they fit different receptors in your nose. That one's not going to be harmful if you smell one or the other, but sometimes it is, like thalidomide. So some pharmaceuticals are sold as a single enantiomer, and some are sold as a mixture of enantiomers. What if it's sold as a mixture and only one enantiomer is important? Like thalidomide, that example is a little bit different. You could read more online if you'd like. But thalidomide had one good enantiomer, one bad enantiomer. If you could have sold thalidomide as a single enantiomer, it might have gone well. But sometimes our body converts one enantiomer to the other on its own. Sometimes our body doesn't have any binding with the other enantiomer, the thing that didn't bind to substrate. Or sometimes it does bad stuff like the teratogen. Ibuprofen is a famous example of something that's sold as a mixture of enantiomers. It's actually marketed as a long-lasting pain reliever because it participates in bullet number 2. One enantiomer, and I forget which it is, sadly, one enantiomer of ibuprofen fits your pain receptors immediately. The moment you take a pill, maybe not the moment, as soon as you take a pill, it starts going to work and it fits your pain receptors to give you some relief quickly. But the other enantiomer that's also wrapped up in that very same pill, your body converts it to the active enantiomer over a long extended period of time, and that allows more of the active form to circulate in your bloodstream over a longer period of time than what was originally dosed in the little pill that you took. Kind of cool. Before I go away from here, any thoughts on why this might be called ibuprofen? Ibuprofen? Yeah, okay. Okay, so superimposable, non-superimposable is all about mirror images of compounds. We need to be able to look at a mirror image and determine if that mirror image would be capable of aligning, being manipulated and aligning with the original molecule. How do you do this on paper? If I pick up that mirror image, I'm motioning with all my hands over here, you just can't see me. If I pick up that image, there it is, and I rotate 180 degrees around this bromine bond. 180 degrees means that ethyl would swing around to be in the plane on the other side. Bromine's going to stay steady. That ethyl swings around 180 that direction. This methyl is now pointed in the back over there. We'll circle it so that you can tell the difference. And the other methyl is now pointed toward you. Can this compound that I've drawn, that compound, can this compound be aligned on top of that compound? Yes. What we would say is that mirror image is superimposable on this original image, and because it is superimposable, that molecule is achiral, also known as optically inactive, which also means it does not possess any enantiomers. An enantiomer of this molecule does not exist. Now, this compound is said to have a plane of symmetry. Where is that plane of symmetry? It's through the middle of the bromine, through the middle of this carbon and those two carbons. And it would reflect the two methyls back at each other. Chiral, achiral, all about superimposable or not. So, if I pick up this mirror image, there it is, and I rotate 180 degrees, just like I did the last one. I'm holding on to the bromine and I'm twisting the ethyl-methyl stuff around. That's what I get. Does this molecule, can I pick up this molecule and directly match it on top of that one? No. The H and the methyl do not align. There is no way you can manipulate this mirror image to match this molecule. Because of that, it's non-superimposable. Because of that, it's called chiral. Because of that, it's called optically active. Maybe you get the point. How can I tell if something is going to be optically active or not? We're searching for things that have asymmetric carbons. What is an asymmetric carbon? A carbon bonded to 4 different groups. So this is my asymmetric carbon, because that carbon is connected to a bromine, a hydrogen, a carbon, and a carbon. Wait, what? If I had a little record, yep, bromine, hydrogen, carbon, and carbon. You said it's bonded to 4 different groups. I did. This is a CH3. This is a CH2CH3. Are those identical? No. They do have the same atom, carbon and carbon, but this carbon is different from that carbon because of their neighbors. This is a CH3, CH2, CH3. They're different. Different branches means it is an asymmetric carbon. Anything that has a single asymmetric carbon has 2 enantiomers. Another word for asymmetric carbon is a chirality center. That word is a lot older. It's not used in most chemistry contexts now, but it may still be used in other formats like an MCAT or something. I really don't know. But chiral compounds cannot possess a plane of symmetry. This molecule does not have a plane of symmetry. Okay. So we've talked about an asymmetric center, an asymmetric carbon, and a stereocenter. What's the real difference? There's the 2 definitions for you again. But I think that it's kind of important to draw a little Venn diagram. A little Venn diagram that looks like a fried egg. In the center of that Venn diagram is an asymmetric carbon. Out here is the stereocenter thing. What that says is every asymmetric carbon is a stereocenter, but not every stereocenter is an asymmetric carbon. So a good example of stereocenters that are not asymmetric carbons are these that are all highlighted in purple. You have to be bonded to 4 different groups to be an asymmetric carbon, and this is not even bonded to 4 different groups. So that cannot be an asymmetric carbon. We'll talk more about examples like this in a moment. But this is an asymmetric carbon, but also a stereocenter. Keep the terms separate. It's important. I've said this a time or 2, but I thought it was worth writing down. Yeah? Okay. So the big picture of why we care is all about biochemical recognition stuff. But the small picture that's easier for us to process and learn about these things are when we compare molecules like these to decide, are they the same or are they different? Because we need to be able to recognize, are they the same or are they different? If I tried to superimpose this image onto that one, would it match or not? If I tried to superimpose this image onto that one, would it match or not? What about this last one? It's different from those other three. What if I tried to superimpose any of those on this last image? Does it match or not? Those are hard questions to answer when you're just trying to look at them and manipulate them in your mind's eye. One of the reasons we talked about Newmans throughout this chapter is because we're going to have to do manipulations like that to see if these molecules are the same or not. Oh boy, it'll be great. If you thought comparing these perspective drawings was fun, just wait till we toss in other types of compounds, other types of drawings, like these. These bottoms we recognize are what kind? Newmans. We need to be able to see if these Newmans match each other, but also if these Newmans match the perspectives on the previous slide. These top structures are called Fisher projections. Fisher projections have a weird setup. They're drawn with everything as a straight line, like everything is all in the same plane, but we know that's not true. A Fisher projection has a bow tie across the middle. Every carbon center across a Fisher projection, every single one, every carbon center has a bow tie across the middle. Okay, if there's a bow tie that direction, you just told me I can't draw things that way. Yep, we also have dashed bonds all along the vertical. So a Fisher projection often has multiple horizontal slats like that, but across every horizontal slat is a bow tie. Those things are all coming out toward you, and down every vertical is going away. So a Fisher projection is drawn like everything is flat in the same plane 90 degrees. Not at all. It's still a tetrahedral carbon because it's sp3. It still has a 1 of 9.5 degree bond angle. It's just we represent it in a super weird way. So in these Fisher projections, we need to be able to tell if these molecules are the same compared to each other, the top two Fishers, or if these are the same as the Newmans, etc., etc. I think you get the point. It's really difficult to just pick up molecules and rotate them and see if they're the same or not. Most people don't love that type of approach of just picking it up, manipulating it in your mind, and seeing if they match or not. They want more confidence that their answers are correct. In comes absolute configuration. So you've seen these being used in the examples we just discussed, but let's explain how these absolute configurations are assigned. So absolute configurations means R and S, the stuff we just said. So an absolute configuration can only be assigned around an asymmetric carbon. An asymmetric carbon is what? Bonded to 4 different groups. So you should assign priorities to the 4 different groups that are around that carbon using the Cahn-Ingold-Prelog system of priorities. You know, those things we just learned for alkenes? Good news is you get to use the same rule set for asymmetric carbons. So assign priorities, orient the lowest priority away from you. We should put a little asterisk by that maybe because we're going to talk further details about that. But put the lowest priority away from you, as in on the dash, and then trace your priorities 1 to 2 to 3. If you go clockwise 1 to 2 to 3, it's R. If you go counterclockwise, it's S. Let's walk through some examples to see if we understand this at all. So the first rule of Cahn-Ingold-Prelog is higher atomic number, higher priority. I guess before I even say that, I should say look at your molecules and find asymmetric carbons. These are all 2-bromobutane, which is what we've been discussing since the beginning. So this carbon is the asymmetric carbon in each of these. So what are the 4 different groups? The 4 different groups are Br, carbon, carbon, hydrogen. But one of the carbons is a CH3, and one of the carbons is a CH2CH3. Those are my 4 different groups that I need to assign priorities to. So if I take this first one, I'm comparing Br, carbon, carbon, hydrogen. Higher atomic number gets higher priority, so bromine is priority number 1. Hydrogen is priority number 4. Carbon and carbon are priority 2 and 3, but I need to figure out which one is priority 2 and which one is priority 3. So this carbon is connected to 2 hydrogens and another carbon. This carbon is connected to 3 hydrogens. So we're following the path to find the first point of difference. If you're following the rules as outlined earlier, where we're tied, as in carbon versus carbon, we're following the path to find the first point of difference. So if I compare these, hydrogen, hydrogen, same, hydrogen, hydrogen, same, but hydrogen versus carbon, those are different. So then I re-look at my rules. Higher atomic number, higher priority. So that makes the ethyl group priority number 2 and the methyl group priority number 3. Before I trace, I need to double check. Number 4 in the back? Yep. 1 to 2 to 3, that's clockwise. So this molecule is R, 2-bromobutane. Yep. It was a little bit painful to go through all the priorities the first time through, but since all of these molecules are 2-bromobutane, I know Br is 1, hydrogen is 4, because of the way we just stepped through it. Ethyl is 2, methyl is 3, 1 to 2 to 3. The lowest priority is oriented away from me. This is S, 2-bromobutane. Could you tell that these were different molecules previously? Maybe. If you look at them, they've got a lot of decoration on them now, but you could maybe see that they are mirror images of each other. That's what I'm trying to show a mirror with this dashed line. They are mirror images of each other the way they're oriented. And knowing that a compound has an asymmetric carbon, when you recognize that 2 compounds are mirror images of each other, that's one quick way to say these are enantiomers. I'm not sure we've actually defined enantiomers yet. Maybe now's the time to do that. Enantiomers have the opposite configuration at every chirality center. So if I have an R and an S compound, those are enantiomers. We're going to get to molecules that have more than one asymmetric carbon in a moment, but for now we're sticking with things that have one asymmetric carbon. Anything that has one asymmetric carbon has 2 enantiomers, 2 stereoisomers that exist, and they are enantiomers. Ooh, that was a lot of words. Good news down here, it's the same example. So I can do 1, 2, 3, 4. I check, my lowest priority is, no, my lowest priority is not oriented away. So the official Conning-Gold-Prelog rules say the lowest priority needs to be away, but there is a shortcut. You can say 1 to 2 to 3, like that. 1 to 2 to 3, that's clockwise. That looks like this is going to be an R compound, but, don't fall asleep on me now, but my lowest priority is coming toward me. My lowest priority is the opposite of what the rules say it needs to be. So that means my compound is really an S enantiomer. It is not the R enantiomer. It is the S enantiomer. I'm going to repeat that. Because my lowest priority is coming toward me, it's the opposite of what the rules say it's supposed to be. So that means the absolute configuration is the opposite of what it looks like. Yeah? Okay. We've got a bromine, a methyl. Nope, that's an ethyl. A methyl, a hydrogen. My lowest priority is not oriented away. Also, my lowest priority is not oriented toward. I have a rule that says it can be away, or we just walked through an example where it's the opposite of away, aka toward. But this lowest priority is in the plane. There is no rule and no trick and no shortcut. Well, there is a shortcut. There's no rule, no trick for saying when it's in the plane, 1 to 2 to 3, go this direction, it's that. No way. When it's in the plane, you have 2 options. Number 1 option, we're going to call it unplug. Number 2 option, we're going to call it rotate. it's a personal preference on what you would like to do. I'm going to walk through both possibilities right now. If I say unplug, that's taking advantage of the definition of a stereocenter. A stereocenter is an atom upon which interchange of any two groups generates a stereoisomer. So if I unplug, and I can choose what to unplug, but I'm going to unplug to make things as advantageous as possible. So I'm going to plug the methyl in where the hydrogen was, and the hydrogen in where the methyl was. Why would I do that? Because my rules officially say the lowest priority needs to be away from you. So that's why I chose to unplug the thing that was away from me and the fourth priority and swap those. So if I unplug those, 1, 4, 2, 3. If you must pass someone on your journey from 1 to 2 to 3, it has to be priority number 4. Do not pass number 3 on your journey toward number 2. Maybe that makes sense. Maybe that doesn't. Maybe you should rewind and repeat. I don't know. So 1 to 2 to 3, lowest priority away, that's clockwise. This is an R enantiomer, which means before I unplugged, that was an S enantiomer. Why? Because a stereocenter is an atom upon which interchange of any two groups generates a stereoisomer. And you say, I'm tired of you repeating the same definition. I still don't understand it this time either. I unplugged two of these groups. I interchanged those two groups. And when I interchanged those two groups, I made the enantiomer compound. Yeah? That's unplug. What about rotate? So if I rotate, and I always signify rotating with a little pig's tail curly Q arrow like that. If I rotate, I'm going to hold on to my ethyl, and I'm going to spin my bottom 3 groups around that direction. I want to call it clockwise or counterclockwise, but it depends on the perspective you take as to which one it is. So let's not say. Okay, so I hold on to my ethyls. My ethyl stays up top. And I'm going to push my hydrogen around so that my hydrogen goes to behind the plane over there. That's going to force my bromine to be in the plane over here. That's going to force my methyl to come out of the plane up front. I should have said, and I don't think I did, when I drew my template before I added these 3 groups, I wanted to keep my thing that was in the plane, my dash and my wedge, all in the same relative orientation as they were in my original molecule. I'm just wanting to hop, merry-go-round the atoms that are attached to those 4 different groups. Okay, so here's my 1, 2, 3, 4. 1 to 2 to 3, that's counterclockwise. That looks like S. When you rotate a molecule, you did not interchange any 2 groups. Rotation does not change orientation. So absolutely further confirmation that that molecule was S. When we unplugged, we determined that was S. When we rotate, we confirm that is S. Most students will like one of these approaches better than another. Choose an approach and stick with it. It doesn't matter. I go back and forth, but most students stick with one. When you unplug, it's the opposite of what it looks like. When you rotate, it's the same of what it looks like. Don't confuse those things. So we just spent a while talking about 4 perspective drawings. What about when they're in a different orientation? Whew. Oh boy. Remember, this one up here is called a Fisher projection. I can put my same priorities around there because it's still 2-bromobutane. You would think we've beat this dead horse enough, but not yet. Put my same priorities around there, and I try to go 1 to 2 to 3. It looks like S, but a Fisher projection has a bow tie across the middle. That means my lowest priority is coming toward me, so my lowest priority is the opposite of what the rules say it has to be. So it's the opposite configuration of what it looks like. So it looks counterclockwise. It looks like S. Therefore, it must really be R. Fisher projection wasn't so bad. Newman, that's a different story. Newmans aren't terribly easy, but if you need me to be your cheerleader, I believe in you. So the first thing that I do when I'm trying to convert a Newman to a perspective drawing, why would I do that? Because it's very difficult to try to see orientations in your mind's eye. If you can flex like that, that's fine, do it. But it's very hard to see the orientation in your mind's eye to know if that should be R or S. So what I do is convert the Newman to a perspective drawing. Here's how I do it. I choose a direction to look at the Newman from. So my front carbon is on my right based on the angle that I've chosen to view this. My back carbon is on my left based on the angle I've chosen to view this. On my front carbon, I've got a methyl pointed up in the air, a hydrogen coming toward my eyeball. You see that hydrogen coming toward my eyeball? Yeah, it's coming toward me. I've got a bromine going behind. On the back carbon, I've got a methyl straight down, a hydrogen going toward my eyeball, and a hydrogen going away. The back carbon, the orientation doesn't matter so much. Why not? Because the back carbon is not an asymmetric carbon. The front carbon is an asymmetric carbon. So we really need to worry about the orientation of the groups around the asymmetric carbon because we don't want to accidentally draw the enantiomer of this compound when we're just trying to convert one Newman into a perspective. Okay, so assign priorities. It's the same dang molecule. 1 bromine, 4 hydrogen, 2 ethyl, 3 methyl. 1 to 2 to 3. We have to pass number 4. Can't pass number 3. 1 to 2 to 3. Looks like R. Lowest priority is coming toward me. So that's the opposite of what my rules say. So it's the opposite of what it looks like. This is the S enantiomer. Whew, yeah. How about some examples that are not 2-bromobutane? Wouldn't that be fun? These are more examples to clarify the Kahn-Ingold-Prelog system of priorities. These clarification rules that we're about to do also apply to alkenes, which we've already covered, but we didn't cover many examples of alkenes because if you learn asymmetric carbon Kahn-Ingold-Prelog rules, the exact same things apply to alkenes. They're even simpler because there are 2 groups on alkenes, not 4, like asymmetric carbons. Okay, so Kahn-Ingold-Prelog says highest atomic number, highest priority. Iodine has a higher atomic number than bromine, which has a higher atomic number than chlorine, which has a higher atomic number than hydrogen. Highest atomic number, highest priority. 1 to 2 to 3, lowest priority is in the back. Clockwise, R. That first example was simpler than the next example. In the next example, we're comparing chlorine, bromine, hydrogen, and carbon. That's bromine, not boron. Hydrogen and carbon. Sure, there's an iodine over here, but you're looking at the atom directly attached to the asymmetric carbon. And directly attached is another carbon. So knowing that those are the 4 things I'm considering, bromine, chlorine, carbon, and hydrogen, because it's all about atomic number. A lot of students start thinking it's about the mass of the branch. It's all about the atomic number of the atom directly attached to the asymmetric carbon. Okay, 1 to 2 to 3, that's clockwise. My lowest priority is away. Clockwise is R. In the bottom one down here, I'm comparing chlorine, hydrogen, carbon, and carbon. Highest atomic number, highest priority. That helps me choose chlorine and hydrogen as 1 and 4, but carbon and carbon are tied. This carbon is connected to 2 hydrogens and another carbon. That carbon is connected to 1 hydrogen and another carbon. See why condensed structural formulas mattered? This is one reason it mattered. Hydrogen versus hydrogen, no comparison. Carbon versus carbon, no comparison. Higher atomic number down on the bottom branch means the bottom branch is number 2, and over here is number 3. 1 to 2 to 3, that direction, that's counterclockwise. Lowest priority in the back, counterclockwise, is S. Yeah? Yeah. So the double bond rule in the Kahn-Ingold-Prelog system is a little bit strange. Let me explain. Highest atomic number, highest priority. Here it's chlorine versus carbon versus carbon versus hydrogen. So chlorine and hydrogen chosen. Carbon versus carbon. This carbon is connected to a hydrogen and a carbon. But the double bond rule says pretend like that atom is attached to 2 of the thing that it's double bonded to. So Kahn-Ingold-Prelog rules say we count this carbon twice when we're deciding what this carbon is connected to. Yeah, okay. This carbon is connected to a hydrogen, a carbon, and another carbon. Uh-oh. My top thing and my bottom thing are totally tied. They're both connected to CCH. So then you have to go further down the line, further down the branches. This carbon is connected to 3 hydrogens. That carbon is connected to 3 hydrogens. Okay. I'm running out of space a little bit, but this carbon, that means I'm looking at that one, really. That carbon is connected to 2 hydrogens, but the double bond rule says you retrace your steps. You do not retrace your steps when you're looking at single bonds. The double bond rule says retrace your steps. So it's like this carbon is connected to 2 additional carbons. HHH versus HHC. Winner, winner up here. So we had to go pretty far down the branch to decide that up there with the double bond is priority number 2. And down here with the isopropyl is priority number 3. 1 to 2 to 3, lowest priority away from you. That's clockwise. Clockwise is R. Whew. This is weirding me out over here. Chlorine, hydrogen, those are easy. Then I look at my 2 carbons. This carbon. What is CHO? CHO means aldehyde. This bottom carbon is connected to a hydrogen, oxygen, oxygen, OH, OH. So that's my 2 different branches drawn out so that you can see them. This carbon is connected to an H, O, double bond rule says O again. Whoo! Yeah? This one down at the bottom is connected to an H, an O, and an O. So, tied. Hoo-hoo, tied. You go further down the line and you say this oxygen is connected to a hydrogen, and I'm going to compare that. I'm going to say that this oxygen is also connected to a hydrogen. It's not real great formatting I've chosen down here. But my next layer in the bottom carbon is 2 hydrogens to compare. My next layer up here is this oxygen is considered to be connected to 2 carbons. So comparing 2 hydrogens and 2 carbons, winner all day up here, higher atomic number. So that makes my CHO my aldehyde number 2, my glycol number 3. 1 to 2 to 3. Lowest priority in the back. Clockwise, it's R. A lot of students look at these couple of examples, and they might search for examples online and find that the double bond is often the higher priority than the other chain you're comparing it to. I would stick with often. It is not always. It depends very much on the structure of the remainder of your molecules. So do not make the assumption that the double bond is always higher priority, because sometimes you will get burned. Often, but not always. So there's our little summary on enantiomers. Things that have 1 asymmetric carbon can exist as a pair of enantiomers. Enantiomers always have the same physical properties, which makes them actually very difficult to separate, but they are separable. one way they could possibly be separated is because they interact differently with chiral compounds, you can separate them based on how they interact with a certain chiral compound.